Excuse me. You mean
All right. It's my pleasure to introduce James Tuttle. He's a PhD candidate at Auburn University and conducting his research with Dr. Anita Kelly at the Alabama Fish Farming Center. His research experience encompasses many aspects of aquatic animal health and extension in the catfish and shrimp industries. His dissertation focuses on evaluating disease management strategies for commercially important aquaculture species in the southeastern US. Thanks for being here.
Great. Thank you very much, Dr. Phelps, for the introduction. I hope everybody's doing well this afternoon, and I guess without any further ado, let's get into it. So before I go too far down the rabbit hole, let's talk a little bit about the shrimp industry. Shrimp, in particular, Lithopenes vannamei, or the Pacific white shrimp, is one of the most important aquaculture species globally. And for the U.S., it's also very important. The U.S. imports a very unbalanced amount of shrimp compared to how much they produce via aquaculture. And that incongruence makes it even more difficult when you consider the annual per capita consumption of shrimp is about 5 pounds or greater per person. And there's a lot of benefits to culturing Lithopenes vannamei here in the United States. It's a relatively fast-growing species. It can handle culture in a wide variety of different salinities, anywhere from 2.5 all the way up to 4 or 45 parts per thousand. And also, it can be cultivated in recirculating clear water systems. It can be cultured in extensive ponds, et cetera, et cetera. So, if this species has a lot of benefits to culturing and it's not as labor intensive or compared to other species, and it's a high value species, then why is it not cultured? Well, part of it is due to the issues with bacterial, viral, and parasitic infections with Lithopenes vannamei. Because of its benthic lifestyle and the fact that it does not possess an adaptive immune system, it's very difficult to assess when exactly these shrimp need to receive any kind of antibiotic or any kind of intervention from a producer. And also, due to their life cycle, they experience different levels of stress and different levels of different types of infections that they can tolerate throughout their life cycle. Um, and instead of trying to treat the diseases and infectious agents with things like antibiotics, um, it might be more impactful to try and use a disinfection method rather than trying to develop a pseudo vaccine or a antibiotic that can be used, which both those processes are a lot more expensive. So, what disinfectant could be potentially used for shrimp aquaculture? One of those options is peracetic acid. And Dr. David Strauss from another USD ARS office has done a lot of the research and legwork with regards to looking at the effects of peracetic acid. It's an oxidative compound, which can have up to 35% of the active ingredient, which is the peracetic acid. And as the name would suggest, it's a combination of both acetic acid and hydrogen peroxide, and it's in an aqueous suspension with those two compounds. However, it is very photosensitive, has a short half-life, but it can be an indiscriminate antimicrobial compound, and it's been shown to be effective against viruses, bacteria, fungi, and parasites. And a brief timeline, this compound was first assessed and synthesized back in 1902. And throughout the 20th century and into the 21st century, it has been used in many different types of applications throughout agriculture and also wastewater treatment. And very recently, I want to point your attention to the bottom right corner of the screen. A commercially available compound, Vigorox, has now been approved for cleaning and disinfecting aquaculture tanks and raceways, both when fish are present and then also when fish are present for recirculating systems and also when they are not present. So thanks to a lot of the research from a lot of other aquaculture professionals and professors, there has been a lot of progress made with getting this compound approved for applications in aquaculture. However, currently for shrimp, there are, as far as I'm aware, there are reviews and plans to extend this application and use for shrimp, but are still ongoing. But in a research setting, there has been a lot of work done to assess how effective this can be for aquaculture species, but not a lot for shrimp. And got me thinking maybe this could be a potential tool for shrimp, particularly in low salinity culture. So some of the objectives for this, because this is an oxidative agent, um, wanted to evaluate how effective this is on Lidopenaeus vannamei under different salinities in clear water systems, because not every single system is going to be at the exact same salinity. And then I was also interested in looking at how water parameters change over time once the parasitic acid is added to a system. And then because this is a relatively corrosive and dangerous compound, it was also important to determine LD50 values for little Penaeus vannamei when they are exposed to this parasitic acid. And then also, I felt it was important to look at how effective this compound is at dealing with vibriosis causing bacteria, in particular, some virulent strains of Vibrio parahemolyticus. So, to begin with how I went on addressing these objectives, first thing I wanted to determine was create a dose response curve and also collect some histological data. So, in order to assess which concentrations would be most appropriate for running determining an LD50, um, first, what I would do is place 10 liters of saline system water, either at 4 or 30 parts per thousand, and 3 shrimp into a 5-gallon bucket that was aerated. And then I would create a suspension of dilute parasitic acid and add said suspension to those buckets with geometrically increasing concentrations of parasitic acid. And then throughout a 48-hour period, monitor mortality. Um, and the goal of these range finding tests was to expose a small number of shrimp um, at single concentrations to determine which concentration starting at zero and then again geometrically increasing would I be able to encompass a parasitic acid concentration that resulted in both 0% and 100% mortality. And once I was able to figure out that range and determine that for 40 parts and 30 parts, then I would expand that to set up a complete LD50 trial, which would involve 6 different parasitic acid concentration treatments, including zero. And the buckets would have 10 shrimp in them as opposed to 3. And those buckets would be increased to triplicate. And then the parasitic acid concentration, as well as pH, would be measured at 1, 2, 4, and 24 hours post parasitic acid exposure. And then not only would I want to try and target one size of shrimp for these trials, I felt it was important to look at 2 different life stages of the shrimp. So um, I conducted 4 sets of LD50 trials, one at 4 parts per thousand with roughly 5-gram juvenile shrimp, another 4 parts per thousand trial with PLs, and then again repeating those same 2 trials, but at 30 parts per thousand. So a total of 4 LD50 curves were determined. And then at the end of each LD50 trial, if there were any surviving shrimp, I would want to then fix any whole body individuals for histological analysis to evaluate any physiological effects from the use of parasitic acid. And as far as addressing the growth of bacteria, first, 2 different strains of a highly virulent Vibrio parahemolyticus, or 2 different parahemolyticus isolates were collected from Dr. Craig Shoemaker, and then they were streaked for isolation and grown in marine tryptic soy broth. And then those broths were then exposed to varying levels of parasitic acid, again, with a lot of varying concentrations of parasitic acid. And then those suspensions after 30, 40, and 45 minutes were then plated onto selective Vibrio chromo agar and left to incubate for 10 to 12 hours. And the bacterial colonies were enumerated via drop plate method. So now moving on to the results. So for the first LD50 trial with using PLs at 4 parts per thousand, I was able to determine a estimated LD50 curve with an LD50 value of approximately 44.13 parts per million. And at the conclusion of 24 hours in each of the respective treatment dosage, as you can see on the right, the PAA concentrations from each of those treatments on average were anywhere from 0 to only 2.95 parts per million. So after 24 hours, a good portion or nearly all of the peracetic acid in that bucket was had already broken down. And as far as the pH is concerned, there was initial drop in pH with respect to how much peracetic acid was added, but over time, depending on how much peracetic acid was added, the pH was able to somewhat recover, which then added in another question of what other parameters should we be looking at, but I'll get to those later. And now moving on to the PLs at 30 parts per million. The estimated LD50 value was higher than the ones at 4 parts per thousand, which um, was not too surprising. Um, and then the pH also was very similar to the trend that was shown in the previous slide. And again, also peracetic acid concentrations after 24 hours almost completely broken down. But now we move on to the juveniles at 4 parts per thousand, and the calculated LD50 value was lower than the ones that were determined for the PLs. And because this is a single dose response curve, I've not looked into the other aspects of or which statistical test would be most appropriate to determine the differences because there was another compounding factor that we needed to account for, which was how often the shrimp molt. And that's another question that I'll have to address later. But again, after 24 hours, majority of the peracetic acid had broken down. And again, as you add more peracetic acid, it lowers the pH. But then over time, the pH is able to rebound or recover depending on your alkalinity. But then we get to the juveniles at 30 parts per thousand. And by this time, this was the fourth experiment that had been concluded. And I'd been using the peracetic acid fairly regularly. And it was a little unexpected that I got an LD50 value of over 700 parts per million. And what I suspect happened is, as I mentioned previously, because of the short half-life, the peracetic acid concentration that I had was not accurate. Thus, I needed to scrap this trial and repeat this one at a later date. So now moving on to the results from the drop plate procedures. So on average, the broth cultures produced a concentration of about 3.45 times 10 to the 7 CFUs per ml, which was a fairly healthy inoculum. But at any concentration of peracetic acid, starting at 0.25 parts per million, no growth. So then we decided to push that a little further. Even at concentrations of as low as 0.03125 parts per million of peracetic acid, there was no growth of Vibrio parahemolyticus observed on any of the drop plates at either of these salinities. So regardless of whether it's 4 parts per thousand or 30, even that low concentration of peracetic acid was enough to inhibit growth. So now moving on to any future discussions and considerations. So from these experimental trials, it has been shown to be a reliable tool for shrimp aquaculture, and there seems to be a fairly wide range between the LD50 that was experimentally determined with this throughout this trial, and then also the concentration needed to inhibit bacterial growth. The decreased pH levels and the toxicity are some of the most challenging issues that need to be addressed in future studies. Because issues with molting and as well as determining a relationship between alkalinity and degree of pH change is another thing that needs to be assessed. And then also, what is the most effective way to apply peracetic acid in aquaculture systems to ensure you get the desired result? Or also, how effective is peracetic acid against other vibriosis causing bacteria? But with that, I would like to thank all of my funding sources, as well as Dr. Davis, Craig Shoemaker, the suppliers of the shrimp, as well as multiple research assistants, Jesse James and Sunny Dahl, and a few graduate students that helped me along the way. And with that, I will open the floor to any questions you may have.
Great talk. Thanks a lot, James. We've got a couple of questions here in the chat. Um, First one, were any longer-term toxicity studies conducted, perhaps over several days post-exposure to assess delayed mortality?
Um, so after 48 hours was really the hard cutoff point, particularly when when we had established that there were concentrations that would result in 100% mortality. Um, because at that after 24 hours, majority of the parasitic acid had already broken down. So any latent mortality, it would be difficult to say whether or not the shrimp had succumbed to exposure due to parasitic acid, or if they had succumbed because of the components. So whether it was the prolonged exposure to that low pH, or it could be the acetic acid or the hydrogen peroxide components by themselves. Um, it would be difficult to definitively say those would be the explanations for mortality if we extended it beyond that 48-hour period.
Hmm. Got it. You've got let's see, another couple of questions in the chat, James, but for the sake of time, maybe you could answer those
No
after
problem.
the talk's done here. Thanks again.